Well, clearly we should have booked a much bigger auditorium for Grant's talk. It's wonderful to see so many of you here. My name is Kannan Soundararajan. I go by Sound. I am the chair of the math department, and it's my pleasure to welcome you all to this public lecture. The math department began this lecture series in 2010, and it was initially funded by a generous gift from Professor David Hoffman, a longtime friend of the math department. Since then, we've had 25 lectures in this series. They cover an enormous range of topics, some that are useful, like biology or AI or astronomy, but then also many that are quite exotic, including art, fashion, and mathematical toys. This year, we are very grateful to Jane Street, who have provided invaluable financial support for the series. As you know, these are difficult times for the university in general, and also for the math department in particular. I would greatly welcome your interest in the department, and we would greatly appreciate your support for the math department. You could look at these websites where you will find much information about what we do. But if you send me an email, I'd be very happy to meet with you and tell you more, and also tell you something about the challenges that we face. So let me now turn to today's public lecture. We have a wonderful treat in store for you with Grant Sanderson. Grant is also known as 3Blue1Brown, and he hardly needs an introduction. I think you all know him. He was a math major at Stanford, and he graduated in 2015. I had the pleasure of having Grant in at least a couple of my courses. I think he was in group theory and number theory with me. And at the time, Grant had a very strong interest in number theory. So this was a time when there was a lot of progress on gaps between primes with the work of Yitang Zhang and also James Maynard and Terry Tao afterwards. And Grant was very interested in these and in sieve theory, which is an area with very deceptively simple problems, but which is technically fiendishly hard. So Grant fearlessly took on this problem as part of his senior thesis and was making a great deal of progress. And then in February of 2015, he told me that there was a different project that he'd started, which was coming alive and which was consuming all of his time and energy. So I later figured out that this was his work on MANIM, which is mathematical animation towards making videos. And in March of 2015, the first video in 3Blue1Brown came out, which I think is about e to the I pi being -1. Since then, 3Blue1Brown has become one of the most popular sites for mathematical exposition. Grant has 8 million subscribers almost. He's put out more than 200 videos on the site, and the videos have garnered something like 600 million views, which seems hard to believe, but I think that's correct. Each of Grant's videos is a masterpiece of exposition. They're always exceptionally clear and engaging, and they present material which is oftentimes useful and important, sometimes whimsical, but they are always interesting. Obviously, Grant has many, many fans among the students, but I should also point out that many of my colleagues are also fans of his, like I am too, and I'm delighted that he's here with us today. Please join me in welcoming Grant Sanderson, who will tell us why.
Thank you, Sound, for that very warm introduction. Thanks to the math department for including me, too. It is always a delight to come back to Stanford, any excuse that I have. And thank you, everyone, for coming. I am very pleased with how many of you can cram into this room. Just nobody flag a fire marshal. So I wanted to talk today about high-dimensional spheres. And my understanding of the public lecture series is that it's something that we want to make accessible to the public. And whenever we're talking about high dimensions, there's a little bit of a divide. I feel like there's some people, especially those who are mathematicians or have the instinct of one, where it's abundantly natural, of course, you would be curious about questions of high-dimensional geometry. But then I think for a lot of people, it can raise questions of, like, what are we talking about? Is this actually real? Why would one be curious about this? So I wanted to open just with a very simple warm-up. It's not a simple warm-up question, but a warm-up question to kind of get us thinking in the right terms, where I'm going to start by letting x be some kind of random number. It's going to be a random number somewhere between -1 and 1. We're going to choose it uniformly. And I'm going to also have a second number, y. It's also going to be a random number. We're just going to choose these uniformly. And we might have some questions that I would ask about this. Decently natural question I might ask would be, what's the probability that if you take the squares of these numbers and you add them up, you end up with something less than 1? So you kind of think about this for a moment. You say, OK, for a particular choice, maybe I take their squares, I add them up. I guess the specific choice we have here happens to be bigger than 1, so that wouldn't count. But if you just keep going and you say, how often is it the case that as we make some random selections, we end up smaller than 1? What do you think the answer is going to be? And this kind of question, on the one hand, it's just a kind of random question I could ask about a pair of numbers. But it really begs to be turned into a piece of geometry. It feels almost wrong not to take a question like this and turn it into geometry. Because a natural way that you could think about this is to say for each of your numbers, rather than thinking of them separately, think of them as the coordinates on a two-dimensional plane, x and y. And when you're choosing each one at random, what you're basically doing, if it's, each one is uniform between -1 and 1, basically meaning anything in that range is kind of equally likely. There's no bias towards being in the middle or on the edges. You're choosing a random point inside a square. And then from that perspective, when you say, what's the probability that you add up the squares, you end up smaller than 1, again, it's something that's begging to be turned into a kind of geometry. In this case, that property, add up the squares, make them less than 1, that's the same as saying that the random point that you've chosen is somewhere inside a circle. And the reason for that, it comes from one of the first theorems that any student runs into that's kind of a real bit of math. It's the Pythagorean theorem, where one of the points on that boundary of the circle, if that circle has a radius r, it's going to satisfy x squared plus y squared equals r squared. So if the circle has radius 1, this property that we want is basically saying that radius has to be smaller, so you're somewhere in the circle. And so from this point, that random question brings you to thinking about very geometric quantities. Namely, what's the area of the circle? How does it compare to the area of the square? So in this setting, the probability is going to look like the ratio of those two different areas. We all learn in school, area of a circle is pi times its radius squared. Radius is nicely 1 in this case. Square, 2 by 2. We get something around 78%. All nice and fun. Now I could vary this a little bit. I could say, what if I wasn't choosing just 2 random numbers? What if I was choosing a third random number, z? And I wanted to know, hey, what's the probability that you add all of these up and you end up with something smaller than 1? Again, the question begs to be turned into a piece of geometry. In this case, we can think of that triplet of points as a point in 3-dimensional space. And then when you do that and you ask what's the probability that you end up with something smaller than 1, the thing you find yourself wanting to know is how much of that region inside this cube, where it's bounded from -1 to 1 on all 3 coordinate axes, how much of that is going to exist inside a sphere in this context. And so you find yourself naturally asking not about the area of a circle, but instead you say, hey, what's the volume of that sphere? And how does it compare to the volume of the cube that it's inside? Now this is another formula, maybe you remember, maybe you don't, that the volume of a sphere happens to look like 4/3 pi r cubed. Now if you want, a little bit later in this lecture, we can talk all about why that's true. But if you work it out in this case, you get something around 50%. Now the thing I want to point out, these sorts of questions, you could just ask it if you wanted, not with reference to the geometry. You could just say, I've got 3 numbers, I am adding up their squares, I want to know what's the probability it's less than 1. That is abundantly sensible to ask, even if you don't turn it into geometry. But of course, it feels much more elegant to answer it by giving it some kind of geometrical meaning. And it almost feels wrong not to. Like it would feel somehow a disgrace to what math wants to be to answer this question not ever referencing volume of a sphere. Now the reason I bring that up is that there's no reason you have to stop at 3, right? A mathematician would very naturally ask, hey, what if we had 4? Right? What if we had 4 random numbers, each between -1 and 1, and you wanted this probability? You add up their squares. How often is it bigger than 1? How often is it smaller than 1? a very empirical question. If you code, you could go and write up some code that gives you an empirical answer to this. And brought from the two-dimensional context, brought from the three-dimensional context, a natural question you might want to ask is, hey, is there an equivalent to a sphere, but up in 4 dimensions? And in the same way that we have a notion of this formula for the area of a circle, or this formula for the volume of a sphere, is there some sort of formula that I could get that would give me the, I don't know, the equivalent of volume, but for this 4-dimensional thing, this group of quadruplets of numbers that could answer this question for me? And I want to emphasize, because when mathematicians talk about higher dimensions, I mean, we don't have to stop at 4. I could say, what if we had 100 different numbers? And I ask the same basic question. And mathematician goes off, and they start talking about a 100-dimensional sphere. They're not talking about dimensions necessarily in the sense of the physics that we live in, or spatial dimensions, right? And I think a lot of people, at least from what I can tell, posting things on the internet and seeing certain comments that people will make to geometry about higher dimensions as written on the internet, a lot of people assume that when you're talking about 4 dimensions or 5 dimensions, it's with respect to some kind of physical reality, and they get all metaphysical about it. But really, it's just anytime you have some sort of natural question you might want to ask where there's a list of numbers involved, it often lends itself to be turned geometric. Like in this case, you kind of know what you want the answer to look at. You might not know what the numerical answer is, but you know the kind of thing that you want to be asking, which is whatever a 100-dimensional ball is, what the thing that deserves to be called a 100-dimensional ball, you want to know its volume, or at least the thing that deserves to be called volume for that. You know what the cube should be. This cube it lives inside is going to be 2 by 2 by 2 by 2 by 2 up for the 100 different dimensions that there are. And this is a back and forth that happens so ubiquitously throughout math. It's so woven into the fabric of what mathematics is, what mathematicians do, it almost feels silly to even highlight it. But you have this divide where on one half, sometimes you're working on problems where you have a collection of numbers, or it's natural to coordinate your data to look like some kind of list of numbers. And on the one hand, you could just think of it as a list of numbers. But on the other hand, you can interpret it as a kind of geometry, where a list of numbers looks like some point in that space. So the examples that we'll focus on, just because they tend to be particularly fun, are going to be the circles and the spheres. Things where the numbers, you think about the sums of their squares. And for example, if you set that equal to 1, you constrain your point so that that equals 1. If it's a list of 2 numbers, it's natural to think of that as a circle. If it's a list of 3 numbers, think of it as a sphere. And then anytime we talk about higher dimensional spheres, in some literal sense, all we mean is just lists of numbers that satisfy this certain property. But there's a bunch of very beautiful visual intuition that you can get, or maybe visual intuition that you wish you could have if you could visualize up in those dimensions, that answers questions that actually matter. Now, the problem with this, though, is that while we love visuals, right, we love geometric intuition, it can take something that's very hard, like this probability question. You could answer it without the geometry. You could write a bunch of integrals and do a whole bunch of calculus and get to some kind of answer. But it somehow feels like it's much better to turn it into geometry. The problem is that high-dimensional geometry actually turns out to be very counterintuitive. There are things that start to happen as you scale up the dimensions that are just really unlike anything that you see down in the, the very few number of dimensions that we have any kind of familiarity with, namely 2 and 3 for the most part. So I want to show you a very classic example of this, which really emphasizes the point. So here's this going to work. We're going to have two-dimensional plane to start. I'm going to draw a box. This box is going to be 2 by 2. So I like to think of it where it's centered at the origin, and it goes from -1 to 1 on both the axes. And then I'm going to put a unit circle on each one of the corners, okay? So if we have it in a coordinate space, those corners look like coordinates 1, 1, -1, 1, all of these. I'm going to put a circle with radius 1 on each of those. So they're all kind of kissing each other. And then I'm going to draw a 5th circle in the middle. And I'm going to make the middle one as big as it can be so that it ends up tangent to all those ones that are on the outside. So those outer ones have radius 1. And if I draw one in the middle that has this property where we make it as big as it can be such that it just becomes tangent with those, basic question you could ask, how big is that? How big is that little radius? In this context, 2 dimensions, we know how to answer it. It's going to be very nice, very fun. Again, we use the Pythagorean theorem. So the key quantity you need to know here is the distance to the diagonal part of that square. So you can draw this little right triangle. One side length is 1, the other side length is 1. Using the Pythagorean theorem, you know that that diagonal has to look like square root of 1 squared plus 1 squared, which in this context is just square root of 2. So if that diagonal is the square root of 2, then what does that mean for the little inner circle? How big does its radius have to be? Well, because those corner circles are all radius 1, That means that it ends up being square root of 2 minus 1, and happens to be, 0.414. You look at this, you think, okay, that's all well and good. Why are we talking about this? It's, the kind of geometry exercise maybe one could see in a school class, but what could be interesting here? I say, well, let's see what starts to happen if we step it up. So let's go to 3 dimensions. I'm going to do the same version of this question. So we're going to have a box. It's going to be a 2 by 2 by 2 box. And then I'm going to put a ball on each one of the corners. So each of these balls on the corners is going to have a radius of 1. And I want to play the same game, where I say on the inside of that box, let's put another one, in this case a 9th sphere, and I'm going to make it as big as it needs to be tangent to all of those ones on the corner. And so you might take a little moment in your head right now and think, okay, how big is that inner sphere? How big is it going to be? Again, you want to know the distance to the diagonal of that cube. And in this context, you can extend the Pythagorean theorem. If you know, okay, this diagonal of a square is square root of 2, you can draw a cube. And using the same normal 2-dimensional Pythagorean theorem, you can figure out what that distance across the whole cube has to be. Because we think of this other right triangle that we have here, where one of the bases is this purple line, another one of the legs is this red line, and you have a 2-dimensional triangle, so you don't have to invent a new rule. I actually really want to emphasize this, because we're going to extend the Pythagorean theorem into higher dimensions, and I want to emphasize it's not something where we're just assuming that that's the right way to talk about distance or kind of imposing it. It's something that very naturally arises in this case, where you can talk about this distance in that third direction as being, in this case, the square root of 3. And that's not like an added assumption that we've put onto how we're going to do geometry in 3 dimensions. It arises from the normal Pythagorean theorem. So square root of 3 in this context, which means if we go back to our cube, distance to the corner, square root of 3, which is roughly 1.73 or so. So when you subtract off that 1 for that corner radius, it means that inner sphere has a radius of about 0.7. Again, seems perfectly normal. Nothing to see here. What could go wrong? But the funny thing is what starts to happen as you scale up dimension, like I said. Because that same Pythagorean theorem rule starts to work if we talk about 4 dimensions, 5 dimensions, and all that. And again, these aren't physical dimensions. It doesn't have to be the case there's a space we can walk in. We're just talking about all the different quadruplets of numbers. And so in this context, it can't really draw a 4-dimensional cube, but it would look something like having a cube as its base and then moving in a certain 4th direction that we can't quite think about because all of our 3 are accounted for, but some direction that's perpendicular to all of those, and you'll have some kind of cap at the top. But we can use that same extension of the Pythagorean theorem, not imposing any new rules, and say that the distance to the corner from one corner to the other, completely opposite of it, should look like the square root of 4, which is actually nice. In this case, it's a rational number. It gives us 2. So whatever this diagram should look like in 4 dimensions, which we can't really draw, where you're going to have 16 different hyperspheres sitting on the corner, turns out that inner radius, actually it's really nice. That inner radius ends up being 1. So the inner sphere is kind of exactly the same size as the spheres all on the outside of it. So that's cute. So far, it just seems like 4 dimensions, nothing counterintuitive is happening, just kind of cute. But it gets very, very weird if you start to think about how this scales. Because let's say you get a number of dimensions that grows and grows and grows. This distance to that diagonal just keeps growing and growing and growing. So as an example, let's say you plug in 10. Let's think really deeply what's going to happen in this whole diagram if we're in 10 dimensions. Now, I can't visualize 10 dimensions. I don't even think it makes sense to try to visualize 10 dimensions. But we can conclude what's going to happen here. Distance to that diagonal looks like root n. Root n minus 1, in this case, plugging in 10, is going to be a little bigger than 2. And now, as a numerical fact, you might look at that and say, okay, a little bigger than 2, who cares? But let's think about what that means. Let me draw in the second dimensional case a box that's bounding all of the spheres. Okay, so we put these circles on the corner, and I'm going to make this bigger box. It's 4 by 4 by 4, right? If you're going to walk just to the edge of that box, so you walk just in the x direction and you get to the edge of that box, that distance would only be 2. So if that inner sphere is going to have a radius that's even bigger than 2, then in some strange sense up in 10 dimensions, it's actually poking outside of that. So here's what that picture would look like in 3 dimensions. Again, it's this 4 by 4 by 4 bounding box that's sitting outside of all of the corner spheres. And in 3 dimensions and in 2 dimensions, it is so manifestly obvious that that inner sphere, the one in the middle, is not only inside that original box, it's of course, quote unquote, of course inside this bounding box outside of all of them. And yet, what the math is telling us is that this radius for that inner sphere, or at this point it starts to feel questionable if we should even call it an inner sphere, but the radius for that middle sphere, it's not just bigger than all the corner spheres, it's big enough to poke outside of this boundary box from all of them. Now that's just bizarre. And so like I said, this is a somewhat classic example, and I've seen people write about this and say that it suggests that high-dimensional spheres are quote-unquote spiky. I actually really dislike that. The spheres are not spiky. Spheres are as smooth can be. Like, they're lovely. In all of the dimensions, they're as lovely as you could hope. Because by definition, they're all the points that are the same distance from a given center. Spikiness insinuates that, at some points you go out a little farther. Spheres are not the things that are messed up. Do you know what's messed up? It's the cubes. The cubes are messed up. They're very, very weird in high dimensions. Like, schematically for this example, here's how I hold it in my head. So if you have some kind of box, I'm drawing it in 2 dimensions, but in principle a box that's in many dimensions, then if you just want to walk to its edge, you're walking in 1 dimension. And in the examples that I was doing, from the center to the edge, that was always 1, right? But to get to the corner, that corner is actually really far away. See, in 2 dimensions, we just have to, you go in the x direction, you go in the y direction, and sure, you have a shortcut that makes the distance square root of 2 instead of 2, but that shortcut can only do so much. If you're in 3 dimensions, you would have to go in an x direction, a y direction, a z direction, and sure, you have a shortcut, but it only gives you this kind of square root. But the loose schematic, and take this picture with a grain of salt that I have, is for a high-dimensional box, that corner is actually really, really far away, right? So even though the edge remains quite close, the corner is really, really far away from you. And the bigger n, it can be really quite far away. So if you're in, let's say, 10,000 dimensions, that distance to get to the corner is 100. And it kind of makes sense when you think about it, because to get to the corner, you have to go along your first dimension, and then your second, and then your third, and then your fourth, and then your fifth, and on and on and on. And sure, there's a shortcut if you go directly rather than perpendicular each time, but the shortcut can only get you so much. So the whole example that I was just drawing, very vaguely, here's how you might think about it. On each one of the corners of this really high-dimensional box, you have a small little unit sphere. But those unit spheres are just really small in comparison, because they only have a radius of 1. But again, those corners are so far away. And what this would suggest is when you want to draw that inner sphere that's big enough to be tangent to them, it's got to get really big, because it's got to reach that corner that's just so far away, right? So it's an enormous sphere that sits on the inside if we're up in 10 dimensions or 100 dimensions. And the thing that this diagram doesn't quite capture is here there's only 4 corners, because I'm drawing it in 2 dimensions, right? So there's 4 corners. But in n dimensions, there would actually be 2 to the n different corners. So in 3 dimensions, you'd have 8 corners. In 4 dimensions, you'd have 16 corners. So somehow you'd want to hold in your head the idea you've got this thing. And so this is my depiction of what that problem looks like in n dimensions in general. And so it's the cubes that are messed up. And this actually becomes kind of relevant to people who are doing computer science, where you might deal with long lists of numbers. And sometimes it might be natural to, let's say if you're sampling each one at random from 0 to 1, you're naturally thinking of them as inside a cube. But you want to be viscerally aware of the weirdness of cubes and just how far away the corners are. And so it is true that high-dimensional geometry can be counterintuitive. But I want to say it's not necessarily counterintuitive, because what is intuition? Intuition is just drawn from where we live our lives and what we do. So if all the life that we live is in 2 and 3 dimensions, then of course there's going to be counterintuition here. But you can still engage with high-dimensional questions. And I think a lot of mathematicians, they don't build up an intuition of high dimensions in the sense of, they close their eyes and they visualize what it would be like to frolic around on a 5-dimensional cloud. Instead, it's more that there's certain qualitative facts, for example, about high-dimensional spheres that seem a little strange at first, but come to feel like second nature. And so, like I said, anytime you run into something where you've got these collections of numbers, so maybe it looks like this problem I opened with all of the randomness, you might find yourself wanting to ask geometric questions, things like volume, things like what are the angles between different directions. And by the way, on this particular question, there is a really nice way to answer it in general for higher dimensions. So there's a formula that really nicely describes the volume of balls in higher dimensions. And it's one of these most beautiful formulas that we don't see in school. Like, we might learn the area of a circle, or we might learn the volume of a sphere, but very rarely do we learn that there's this combination, this combined fact that kind of generalizes it across all dimensions. It takes a little bit of explaining, though, to even parse what the expression is saying. And before I gave this talk, I got an email from one of the beloved members of the Stanford math faculty, Ravi Vakil, where he's like, oh, I saw you talking about higher dimensional spheres. Just want to, throw out there, one of my favorite facts about high dimensional spheres is this volume formula. And he goes away. I'm like, yeah, that is a nice fact. And then I got sucked into this rabbit hole where I was like, what's the nicest way to explain that fact to people? Like, what's a way that it could feel rediscovered and not just like something that we're handing down from on high? And the thing is, I also had a different plan for what I wanted to do here. And so I'm going to do a little experiment where we're going to do a choose your own adventure talk, where we have plan A and we have plan B. So plan A, where I was going to go with this, and where I can, we could still do this, is talk about the relevance of high-dimensional geometry, in particular to large language models and modern AI. I mean, that's in vogue right now, right? Let's talk about some AI and what that has to do. Alternatively, I was nerd-sniped into trying to think, what's the best way that we could explain this volume formula for high-dimensional balls and make it feel like it could be rediscovered to the audience? I genuinely can't decide. We do not have time for both. So we're going to put it to a vote. All right, so to be clear, your two options. We've got one, which is plan A, which was relevance of high-dimensional sphere facts qualitatively to machine learning. And then choice B is going to be the quantitative fact of specifically what are the volumes of these balls and why does it fit a certain surprisingly nice formula. Let's see. So we've got ourselves A. We've got language models. That's going to be choice A. We're going to put this to a vote. Language models will be A. What I was nerd-sniped into, volumes, is choice B. All right, so everyone's clearing them? All right, so we're going to do it by raise of hands. How many people would like the talk to diverge into choice A? We'll do raise of hands. All right, I can't quite count. And then B, raise of hands. All right, we've got B. Ravi Vakil wins. All right. Great, this is fun. You'll understand this is not, well, of course it's prepared. I prepare everything I do. But let's go, let's do it. Okay, step one for this, we're gonna talk about some specific formulas, and then the way that we get those specific formulas, we're gonna generalize. So we're gonna start with one of my favorites. This is one that you might have seen in school, which is the surface area of a sphere, okay? So rather than talking about volume of the interior, talking about the surface area. It has a really nice formula. It looks like 4 pi r cubed, which is always the suspiciously clean formula because it's exactly 4 times the area of a circle. And I want to show you one of my favorite proofs for why that's the case, why the surface area of a sphere happens to look like 4 pi r squared. So here's how it looks. This dates all the way back to Archimedes. The idea is, let's say you take a sphere, and then we're going to do this projection where we take each point of it, and we're going to project it out onto a cylinder that has the same radius as the sphere. And the cylinder is going to have a height which is 2 times that radius. Now the surprising fact is that that motion, which really warps all of the shapes inside, actually preserves the area. So specifically, if you take a little patch of area, right, so a little patch of area here, and then you let it undergo this projection, then on the one hand, it gets stretched out in one direction. So kind of as you go left to right on it, that gets stretched out as it goes to this bigger radius of the cylinder around it. But on the other hand, it gets squished down because it's coming in at an angle. And it turns out both of those two effects will cancel out perfectly. So let's do this, let's dig into this a little bit more exactly to talk about why they cancel out. So let's put some labels to things. We're going to say that big R is the radius of the whole sphere, and then D is going to be the distance at the particular point that we've chosen to that little patch of area that I'm highlighting. And so the first question I might ask is, how much does it get stretched out along the base of it in this direction? And for this, you can draw a pair of similar triangles, where as it gets projected out, you've got these 2 similar triangles where for one of them, it's got this side length of D, but then for the similar one on the projection, the corresponding side length is going to be R, big R, the radius of the sphere. And so that tells you that the extent to which it gets stretched out looks like big R over D. All very nice. Now let's talk about how much it gets squished in the other direction. And what I mean by squished here is you're taking this projection of something that's sitting at an angle, and so this little line that I'm drawing would be the approximation for its height. Of course, in reality, it's curved, right? It's not really a straight line, but we're gonna model it with a straight line and say whatever we're doing is a little bit wrong, but it becomes less wrong as we make things smaller and smaller and smaller. The error between what we say and what is true is going to get smaller and smaller and smaller as you look at finer and finer little pieces. So that little projection, it turns out that triangle that you can draw, and this is a fun little trigonometry exercise, ends up being similar to this triangle right here. So it's not obvious at first, but you can do a little bit of angle chasing. So if you say, what's the angle between the red line we have here and the z-axis, and you kind of see what it implies, what you find is that this big brown triangle here turns out to be similar to that little blue triangle that was what we drew for that projection. And what you end up concluding is that the extent to which it gets squished down in that other direction also looks like the ratio between this little value d and then the radius of the sphere r. So the two different effects happening on this tiny little patch of area, stretched in one direction, squished down in another, they perfectly cancel. So if you think of the sphere as composed of combining all of these different patches, and again, this is going to be wrong, but if you take finer and finer approximations, the percent error gets less and less bad. Then when you do this projection out onto the cylinder, the areas should be the same. It's a different shape, they all got warped, but the areas should be the same. This is really nice, because the cylinder is something that we can pretty much just unwrap as if it was a piece of paper. You take that cylinder, you imagine cutting it with some scissors, you unwrap it in front of you, and you can turn it into a rectangle. And you know how to take the area of that rectangle. Because when you ask, where did that width of the rectangle come from, it was the circumference, and that's 2 pi r. This is basically the definition of pi. What is pi? It's the ratio of a circumference of a circle to its diameter. And so 2 pi times the radius, which is pi times the diameter, that's going to give you that, that top length. And then the height is just 2 times the radius. So the whole expression here ends up being, ends up being 4 pi r squared. And I'm going to start drawing this inside a little diagram that we're going to fill out here to talk about all the different dimensional questions we might care about. And just to kind of make clear what this diagram is meant to be showing so far, in one of the cells, I'm going to show 2 pi r, and this is going to correspond to, in 2 dimensions, the mass that we want to give to the boundary of a circle, so just the circumference of a circle. So I'm going to put boundary stuff up on this top row, and then the contents is going to come in the lower row. So for example, in 2 dimensions, the interior of that sphere, the area, looks like pi r squared. And so then in our column for 3 dimensions, the thing we just figured out, that we just went through, is that 4 pi r squared gives us the surface area of that sphere. And then the interior of it, which I have yet to explain, is that 4/3 pi r cubed gives you the volume on the inside. And the notation I'm going to use for this to label my 2 different columns, I'm going to say b sub n, or b superscript n, is going to be a ball in n dimensions. So by a ball in 2 dimensions, I mean a circle. By a ball in 3 dimensions, I mean the thing that everyone thinks of when you use the word ball. But we want to use it much more generally for many more dimensions. And then this little del symbol here, I'm going to use to talk about the boundary. So the boundary of a 2-dimensional ball is just a fancy way of saying circle. Or the boundary of a 3-dimensional ball, that's a sphere. It's the surface part. And so we're going to need to understand both of these parts together, right? So like I said, we just went through a little understanding for the surface area of it. And if you want to go from the surface area to the volume of it, now I wanted to do some kind of explanation of this that is as minimal calculus as possible, but there's just a little bit of calculus that does range in here. And technically, I know these are supposed to be, talks for the public in general. Out of curiosity, raise of hands, how many people have not taken a calculus class before? Which is totally fine. Totally. Okay. I figured it might be a safe bet. Whoever's coming to this talk might be a little more fluent. So a thing that everyone who's taken a calculus class drills into themselves through a bunch of exercises is the idea of derivatives of polynomial terms. And this is a thing that it's just in your bones, right? When you take a calculus class, where you see something like r cubed, and the way you think about a derivative is to let that 3 kind of hop in front, and it leaves behind 1 less than itself. R to the 4th, that 4 kind of hops in front and leaves behind a number 1 less than itself. Now, even if you've taken a calculus class, have you ever noticed how if you look at the formulas for the area of a circle compared to the circumference of a circle, one of them is the derivative of the other? Now, that's actually not a coincidence. If anything, I think this is one of the best ways that you can even introduce what derivatives are. It's a very fun example to use if you ever find yourself teaching someone calculus, what the meaning of a derivative is. Because if you think about the area of a circle, the natural question you would ask for this is to say, suppose I increase the radius of that circle by just a little bit. We're going to call that little bit dr. And I want to know, how does that affect the area of the circle? Approximately, that new area that you've introduced, this red portion around. Approximately, it's going to be the circumference multiplied by that thickness. Now again, it's not exact, but it gets less wrong as you allow that, that little value dr to get smaller and smaller. Now there's people in the math department here who might yell at me for referencing the dAs and the drs the way that I am now, but it's my talk, I get to do what I want. So the ratio between that little change in area and that little change in radius here is approximately the circumference, 2 pi r. And the other fun thing about this, when you take a calculus class, you learn this opposite operation known as integration, and you pretty much just do the opposite. Now, I do want to emphasize it because we are going to use this rule. So if you see some sort of polynomial term where you're raised to a certain power, the idea is you increase what that power is, but then you divide by what that new exponent is. So as you go from r cubed to integrate it, you increase that power and then you divide by that. That's the one thing that we are going to use here in a moment as we try to derive this, this general formula. And so you see this by the fact that if you integrate one of these, you get to the other. And again, there's a really nice way to think about this. Integrating, you're bringing together a whole bunch of little circles, and if each one of those little circles you multiply by a little thickness, as you add together all of those little areas, that gives you the area of the final circle. That's the loose way you want to hold it in your mind. Now, you might have noticed, if you have looked at the formulas for the volume of a sphere and the surface area of a sphere, the same fact works. And it's for the same reason, basically. If you take a derivative of that volume expression, imagine letting your little 3 hop down and leave behind 1 less than itself, you get this nice cancellation. And again, it's not a coincidence. You can think of it in your mind by saying, well, what if we had a sphere? What if we knew its volume? And I just increased that radius by a little bit, right? I increased it by a little dr. What do I expect will happen to the volume? Well, the newly introduced volume looks like a shell outside of it. And if you have a small enough dr, then it is not a terrible approximation to say that the volume of that shell looks like the surface area of the sphere, but multiplied by that thickness. And so the ratio between those is what gets you the derivative. What this does for us is it says, if you know the value in one row of this diagram, for example, if you know the volume at the boundary, you automatically know how to get to the other row. You automatically know the interior, because you could just integrate to go from the top row to the second row, or you could take a derivative to go from the second row to the first row. Great, so that's the only calculus that we'll need. If that's all the calculus you have, you can discover this most delightful gem of geometry, which is a formula to unify all of the volumes. And before we get there, actually, I want to talk about not the higher dimensional stuff, but something that might seem a little bit more banal, which is the oft-forgotten dimension 1. The delightful dimension of 1, where it seems a little bit silly to talk about a one-dimensional ball, but if you think about what we mean by ball, we mean everything within a certain radius of a center point. So in one dimension, everything within a certain radius just looks like a line segment. And what is the mass of that ball? How do we want to measure the interior of that? Well, it's just the length. In this context, that's going to be 2 times r. And now if we follow our same derivative rule, and I ask, what should we assign to the mass of the boundary of a one-dimensional ball? Well, what's the boundary of this, line segment? It's just a pair of points. It's 2 different points. And at least following our rule of taking derivatives, we would land on 2. And I hope you agree, that's not an unreasonable thing to say. What should we say for the 0-dimensional volume of the boundary of a 1 ball? Sounds like a weird sentence, but hopefully it doesn't sound that weird in this context. Well, it's just 2 different points. In 0 dimensions, maybe the proper way to talk about volumes is just to count. So at the very least, it makes the rules fit well. But now for the fun stuff. Now for the reason that everybody raised their hand to steer me off course, which is how on earth do we think about these higher dimensional cases? And the trick is to basically generalize what we did. We're going to generalize that Archimedean trick where we're able to take the surface area of a sphere, this boundary in 1 dimension, and then somehow do this projection that let us understand what its area was. But this is a little bit of a puzzle, because it seems quintessentially 3-dimensional, that little trick that we did. And it's not entirely clear what that would mean, what that should look like in a higher dimension. So what I want to try to convince you of is that the right way to think about that move, even though it didn't look like it at first, the right way to think about that move is that we were actually making a knight's move in this diagram. I know that sounds weird. It sounds weird, but bear with me. I think this will make sense. So it's a knight's move where we were going from this interior of a one-dimensional ball, that 2r, and we were getting up here. And the way we did it was by multiplying by the circumference of a circle. So this red square, that's always going to be something that we're multiplying by. Even as we move up in dimensions, we're always going to be thinking about just the 2 pi r from a circle. But the knight's move is really what's going to let us get from one part to another. So when we did this unwrapping of the cylinder, and we ended up with these two different quantities that we were multiplying by each other, take a moment to think about where those quantities really came from. One of them was coming from a circle, and then one of them was coming from an interval, the z-axis in this case. And one way that you could think about this, so I've got this diagrammatic description. Let's say we think about the boundary of a three-dimensional ball as all of the three numbers x, y, z, all the triplets of numbers, so when you add up their squares, you get to 1. That's really what we mean by the boundary of a three-dimensional ball. I'm writing it this way so that we can write it similarly for the higher dimensions when it feels a little bit more abstract. So all we mean, 3 numbers, and you add them to 1. Now, if you're trying to say, how can I find 3 numbers where the sum of their squares is equal to 1? A way you could think about making that choice is to first make a choice for z. You say, as long as I choose a value of z where its square is less than or equal to 1, I should be good to go on being able to find another x and y. Once you choose one of those z's, it's going to give you one of the x and y's. And the trick that made this whole Archimedean projection work for us is that we have this association not between a value of x and y that is necessarily going to make this whole sum work, but we were associating with all the values that just have this constant radius. And so loosely, here's what I mean by that. So let's say you've got this sphere, right? And I'm going to choose each point by saying, first choose a z-coordinate, this green line here, some point. And then that leaves you with a circle of options, basically all the values x and y, such that x squared plus y squared is going to be 1 minus z squared. But the Archimedean trick was to say, hey, if you care about the areas, rather than that circle, you could also think about projecting that circle out onto the surrounding cylinder. And the area of that surrounding cylinder is going to be the same as the area of your sphere. And this was because there's 2 different directions that are being impacted by that projection. One of them is along the circles, as you were told, like walk along that circle, that gets stretched out a bit. And the other is in the other direction, you had that little shadow. And we talked through all the reasons why one of those stretchings and the other squishings happen to cancel out perfectly. Now, my claim to you, and this is going to be a little, I don't know if you have to suspend disbelief necessarily, but it might take a little bit of squinting to properly believe that this does work, is that you can basically apply the same rule to make any Knight's move. And as an example, let's think about the 4-dimensional case. All right, so what do we mean in 4 dimensions? The boundary of a 4-dimensional ball, all I mean by that, every possible quadruplet of numbers, x, y, z, w, where as you add up their squares, it's equal to 1. Okay, we got that. That's what a 4-dimensional ball boundary is even defined to be. The way we're going to think about it is to first make a choice for z and w. As long as your choice for z and w satisfies this condition, z squared plus w squared is less than or equal to 1, you're going to be safe to find some kind of x and y that's going to make this work. So you can choose any value of z and w that sit inside a unit disk of their own. Okay? Any choice of z and w that sits inside this unit disk allows for some other choices of x and y that'll get you the quadruplet of numbers that you want. And I'm thinking of taking this product against not x squared plus y squared with the appropriate radius, where it should look like 1 minus z squared minus w squared. But instead, I'm saying up in 4 dimensions, there's a kind of projection. We can't visualize it quite as easily, but there's going to be an analogous projection where you take these slices. It's going to be a slice that has a constant value of z and w rather than just a constant value of z. That slice is going to look like a 2-dimensional thing, and you're going to get this projection outward. And instead of projecting onto a cylinder, the thing that you're projecting onto is whatever deserves to be called the product of these 2 shapes. Actually, it's a torus. It's very fun. Toruses love to live in 4 dimensions. We won't talk about that too much now. But it's something that deserves to be called the product of these 2 shapes. And because the size of each one of these, because they're independent, so that the critical part of that projection is that this x squared and y squared being 1 means that rather than think of a bunch of circles that are smaller near the poles but bigger near the equator, if you're just thinking about the shape where x squared plus y squared is always equal to 1, z squared plus w squared is less than or equal to 1, the thing that's analogous to a cylinder for us, in the same way you could unwrap that cylinder and you could just say, hey, what's its height multiplied by its width? You can sort of unwrap this in the same way, and the 3-dimensional volume for this boundary is going to end up looking like, well, the circumference of this sphere, that 2 pi r, times the interior of this circle, that pi r squared. Okay, so that, I will admit, it's possible that that's maybe not the most convincing. There's a little bit of hand waving in saying that, but hopefully you agree it's not wildly different from what we were doing in the other case. And if you believed me on that, what that would mean is that you multiply these 2 numbers, And the volume for the boundary of a 4-dimensional sphere, very strange thing to think about. What's fun is it actually picks up another factor of pi, so you end up with 2 pi squared times r cubed. And like I said, if you exist somewhere in one of these rows, you know how to get to the part below it, because you imagine adding together a whole bunch of shells, integrating together a whole bunch of shells. So with just a little sprinkling of calculus, you could say to get from one to the other, all you have to do is integrate the r cubed. And what that looks like is to raise its power, it'll go up to 4, and then you're going to divide by that 4. And so we end up with pi squared divided by 2. Now what I like about this, even if you didn't really believe me here, maybe you thought, I don't really believe that whole Archimedean argument necessarily extends to 4 dimensions in the way that you're claiming. Or maybe you don't even believe that the idea of integrating like this should necessarily work. This claim of this being the volume of a 4-dimensional ball, it's not just some abstract bit of nonsense. It is an empirically testable question. Go to your computer. You could just program up, say, hey, I want 4 different random numbers, put them between -1 and 1, sample a whole bunch of them, right, so that you can get a statistically significant guess at what this probability should be, which geometrically we know we want to be whatever the volume of a 4-dimensional ball is divided by the volume of that cube. So I have a claim for you for what the answer should be based on this formula, and you could check that. So this would be a way that you could check it, see if it ends up being believable, but hopefully that whole line of argumentation doesn't seem too absurd. And if you do that, basically you can keep rolling with this. So it gets a little bit more and more abstract the higher you go, but just to walk through one more of them loosely what it looks like. Let's talk about the boundary of a 5-dimensional ball. What we mean is all possible quintuplets of numbers satisfying this condition. A way that you could think about that is to first choose the last 3. You got to make sure that they're less than or equal to 1. And then that's going to leave you with a circle of possibilities. The claim I'm making is that this Archimedean argument still works to project out such that you're looking at a circle with radius 1. And when you multiply the volume of this ball, which is 4/3 pi r cubed, and r here is just 1, by the circumference of this circle, that 2 pi r, that's going to give us the appropriate entry up in this, this slot here. So it happens to look like 8/3 pi squared r to the 4th. If you do your integration, you end up with 8/15 pi squared. So far, so weird. But you can kind of just leave it on autopilot at this point. I've just given you this little rule, and we can kind of just make these knight moves all the way up. And I'll leave it on autopilot here, and let's just see what we get. So up in 6 dimensions, things get a little bit cleaner, actually, and the volume looks like pi-thirds over 6. We let it run up to 7 dimensions. Things get a little bit uglier again. You do this whole integration. Now we have 105 in the denominator. That seems unwelcome. Certainly does not bode well for a general formula. We go up to 8 dimensions, play the same game. Things get nice again. Looks like pi to the 4th over 24. And the question you might have, even if you understand the whole procedure, you would say, okay, well, what's the general formula? I was promised that there's a nice, beautiful general formula for this, and it's not immediately obvious, although there is whispers of something nice if you just sort of close your eyes to all of the odd dimensions and you just look at the even dimensions. So, there's some hope. But let's see how this might look. So the way I'm going to write this, we know that the volume of a ball in n dimensions, the thing we really care about is the constant that sits in front of your power of r. So, in 2 dimensions, things scale according to r squared. In 3 dimensions, they scale according to r cubed. The things we really care about, these constants. I'm going to give that the name c sub n. So for example, c sub 1 just is 2. That's our very boring 1-dimensional ball. C sub 2 is pi, rock star of the whole story. C sub 3 is 4/3 pi. C sub 4 is kind of the fun one where it's the first indication that maybe pi wants to be even more included in higher dimensional ones. And you just keep going like this. So again, we close our eyes to the odd numbered dimensions because those seem kind of ugly. But the rule that I was just talking about, where we make these knights moves and then we integrate, looks really nice as a formula. Because what we're basically saying, I claim, is that to get the constant in one number of dimensions, you can look 2 dimensions lower, and then you multiply by 2 pi over n. Why 2 pi over n? Well, that 2 pi is what's coming from the knight's move. You're basically taking whatever sits in this square, and you're multiplying it by the circumference of a circle. That's your 2 pi. Why are we dividing by n? That's the integration. So this formula, you could almost read it out as telling us what our little mechanical rule along the diagram was. That 2 pi tells us it's the Archimedean trick. That divide by n tells us that we're integrating. And so as an example, let's say I asked you, hey, we're walking down the street. You're on Stanford. I pull you aside. I'm like, hey, what's the volume of an 8-dimensional ball? You're like, I don't know. But you can figure it out now. Because you say, I don't know the volume of an 8-dimensional ball, but I do know that it can be related to the volume of a 6-dimensional ball. And specifically, I just need to multiply by, well, I said 2 pi over n. By the way, it's actually going to be nice if we push that 2 down. So I'm going to think of multiplying by pi and then put n halves in the denominator. Same thing as multiplying by 2 pi over n, just a different way to write it. So like here in 8 dimensions, the factor is going to look like pi divided by half the dimension. And you say, well, I still don't know the volume of a 6-dimensional ball, but I can figure it out if I could know the volume of a 4-dimensional ball. It's going to be multiplying by pi again, but this time half of 6, which is 3. Don't know the volume of a 4-dimensional ball, but I can figure it out. You just got to step 1 lower on this. Again, you've got that factor of pi on the top, and then half of your dimension, in this case half of 4, is 2. And on the one hand, you could stop here, because now we know the volume of a 2-dimensional ball. But if any of you are in any kind of programming classes, and you are writing a recursive function, and you made your base case 2, everyone would just raise you're a terrible coder. Why would you ever do that, right? Make your base case 0, index at 0. And we actually haven't thought about 0 in this case. So let's just extend the diagram a little bit. Like, what happens if we think about dimension 0 in this case? We know what we want it to be, right? We want this nice recurrence relation t keep working. So it should be something so that when we multiply by pi, we get pi. Like, okay, what would that mean? Okay, we're in 0 dimensions. What is 0 dimensions? Well, I can't move left or right. I can't move up and I can't move anywhere. I'm stuck. I'm just a single point. Okay, 0-dimensional space. It's just a single point. What is a ball? I guess it's everything. A ball is everything in 0 dimensions. How do we count everything? Well, you either have everything or you have nothing. And so everything is the ball. Nothing is the boundary of your ball. We're all in agreement? Okay. So in some perverse sense, Boolean logic is the same thing as 0-dimensional geometry. We're gonna roll with that. But the formula that we now have with appropriately based recursion, right? We're not base casing at 2 like idiots. That actually looks quite nice, right? We got a bunch of factors of pi up on the top, and then down on the bottom, this is just a nice factorial, right? And so we look at this, we say, great, let's package that all together. What we're looking at, if we were doing this for 8 dimensions, is we raise pi to half the dimension, and then we divide by half the dimension factorial. And you know, I said 8, but we could have started anywhere. The same logic would have worked on any of the dimensions. Again, close your eyes to the odds, and it works really beautifully. So we do this, and we can write up a really nice formula for the volume of an n-dimensional ball. It's actually really nice. It looks like pi raised to the half dimension over half the dimension factorial, and of course, everything scales by the dimension. So this is one of those things that feels like it didn't have any business being true. If all you learn, you've got your formulas for area of a circle, volume of a sphere. Even if you saw the next couple, it's really not clear that there's going to be any kind of unifying formula. And again, as I said, you can kind of use this to recurse your way on up through your various dimensions. And as Ravi Vakil said, this is an extremely beautiful formula. And at this point, some of you will be like, okay, it is, but also it makes no sense for odd numbers. For example, let's say I put this out as a proposed formula, and you just say, let's try it out on some of the examples that we know, and you plug in something nice and simple, like, I don't know, 1? Does this make any sense? Now, on the one hand, the recurrence does make sense, right? So like, you should have this instinct that it wants to make sense, because that whole idea of saying to go from one dimension to the next, you pick up a factor of pi, and then you divide by that new dimension over 2. That was just from the whole rule that we talked about, where you make the Knight's move and then you integrate. You do the Archimedean rule and then you integrate. That didn't care about the dimension. That had no bias for even dimensions, right? So we want the rule to work, but the question is if the formula necessarily works. So let's try it. If you plug in something, maybe we plug in n equals 1, what does it look like? All right, so first of all, you're going to have pi to the 1/2, which is the square root of pi. So that's, at the very least, a little weird. And then we have 1/2 factorial, which, I don't know, that doesn't seem like it makes any sense. Because factorials, what is a factorial? You give it a whole number, and then you just keep multiplying on down until you hit 1, right? And so what could it mean to take 1/2 factorial? Well, if you want this formula to be true, right? Like if the universe is going to have any sense of aesthetic beauty with respect to the spheres that it's given you, we know what we want it to equal. Right? We know what we want this to equal. the whole expression has to make it so that our 2 times r expression works. And the only way that that'll make sense is if we define 1/2 factorial to be square root of pi over 2, right? So that, you could do that. There's not really much of a reason you couldn't. You say factorials were only defined for me for whole numbers. I don't know what it should mean for a half integer, but if the universe is going to have any sense of beauty at all, I want it to be this. And then from there, if you have 1/2 factorial, that kind of already tells you what 3/2 factorial and 5/2 factorial and everything should be, because it should just follow the rule that factorials want to follow, which is that to take n factorial, you multiply n by n minus 1. So as long as you have a sensible base case, in this case, I don't know what a programmer would think of you if your base case was n equals 1/2, but in this case, as long as you have a sensible base case, it should work. Now, as it turns out, there is a separate way that mathematicians have extended the notion of factorials. I'm not going to go into too much detail on this one, but it's this thing called the gamma function, and it's defined with a certain integral. And so at this point, there's 2 possibilities for what might happen here. It could be the case that either there is one story of what you want half integer factorials to be based on the sphere story, where you know that 1/2 factorial evidently should be the square root of pi over 2. Feels weird, but you know that's what you want it to be. Now you go, let's say you talk to a mathematician, you look it up on Wikipedia, ask ChatGPT, whatever kids do these days, and you say, what should 1/2 factorial be? And they tell you, well, you should plug it into this whole integral and evaluate it. Now it would be very sad if that turned out to be something different, because that would tell you that I guess there's 2 separate ways that we want to generalize factorials. Luckily, that doesn't happen. It actually does work out. And there's a whole parallel story to this one about a separate way that you could figure out volumes of spheres in higher dimensions that more closely ties you to this particular integral. We sadly don't have time to go into that whole story, but if any of you just are calculus savvy and you enjoy puzzles and you want to noodle this one through, the relevant search term is Gaussian integral. So there's a certain trick for calculating something called the Gaussian integral. And if you think really deeply about doing it in higher dimensions, you're in for a very fun afternoon, and it will justify all of this for you. Okay, but let's step back. We have this general formula, and let's just get kind of a sense of what it's even telling us, what this looks like. So in 0 dimensions, we had a whole existential crisis about it, but we decided it should be 1. In 1 dimension, volume of a unit ball is going to be 2. So in this case, I'm always going to be setting the radius equal to 1. I'm just curious what happens for balls whose radii are 1. 2 dimensions, we know it, we love it. Area of a circle, it looks like pi. 3 dimensions met us at the beginning of the story. It's 4/3 pi. One of our newer friends, 4 dimensions, pi squared over 2. Numerically, that's just a little under 5. 5 dimensions, this one is a little above 5. And if you just stopped here, right? If we hadn't told any story about volumes of higher dimensional balls, and you know that we're asking about volumes of higher dimensional balls, and I show you this chart, you would probably guess that they get bigger, right? Like we're going up in dimension, more dimensions should be bigger in some sense. You would maybe expect that the volumes of unit balls get bigger, but they don't. This is as big as they get. It actually turns around after that point. The next one ends up being a little bit smaller, pi cubed over 6, just a little above 5. The next one, 4.72. The one after that, 4.06. By the time we get down to 10 dimensions, we're back down to around 2. And the general formula, if you think about it in this case, where we're taking pi raised to a certain number, half the dimension, divided by half the dimension factorial. Basically what happens, that factorial term on the bottom starts to dominate. Because on the top, with each, as you go up every other dimension, so if you're kind of skipping a dimension, you keep picking up this factor of pi. But on the bottom, the factors that you're picking up get bigger and bigger and bigger. So it's a little bit bizarre, but as you keep going out, the volumes of unit balls, not only do they get smaller, they actually get really small really fast, right? So it's just really, really, really close to 0. As an example, let's say we talk about the ball up in 100 dimensions, right? How big is a ball with radius 1 up in 100 dimensions? Naively, you might expect it should be a really big number because we're up in 100 dimensions. Or if not a really big number, maybe like a normal sensible number around pi, something like that. But with our new formula, we know that it's pi to the 50 over 50 factorial, which is around 10 to the minus 40. So it's almost nothing, which is very, very weird. And so turning this back to something that is a calculatable, verifiable fact, think of that question I asked you at the very beginning, where we're taking, in this case, 100 random numbers, each between -1 and 1. We're going to square them. We're going to ask, how likely is it that you're less than 1? Now, on the one hand, if you think about it for a moment, it's already kind of intuitive this should be a small number. Because you say all of these numbers could go from anywhere from -1 to 1. So their squares could be anything from 0 to 1. You need all of the squares added up. And there's 100 of them to add up. You need all of them to never exceed 1. So it already feels like, OK, that's kind of going to be some form of coincidence for all of them to be so small that this is the case. But even then, it's not obvious that the volume of the ball itself should be the source of smallness, because we already have a source of smallness. You're dividing out by the volume of that huge, huge, huge cube that's inside of. You're already dividing out by 2 to the 100. So bizarrely, this is telling us you get a small answer. But it's not just a small answer. It's a really small answer. Because you've got this 2 to the 100 on the denominator. And the thing in the numerator is also tiny. It's also on the order of 10 to the -40. So this is one, I said these are facts you could empirically verify. If you went and tried to empirically verify this by code, you couldn't do it, right? Because the number of samples that you would need to, with any kind of significance, get this value, which is just absolutely puny, you're just not going to do it. So in this case, we do actually have to fly more by the theory. Now, I wanted to end by trying to think, like, how do we interpret this value of the unit ball? It's a little bit strange. We look at this. How are we to think about this fact that it's something that initially grows, but then it shrinks, and evidently it shrinks really, really fast? So you step back and you say, OK, what is a unit ball? Like, what do we even mean by the volume of that unit ball? In some sort of literal sense, we're comparing it to the volumes of a unit cube. So no matter what dimension you're in, a 1 by 1 by 1 by 1 by 1 cube should have a volume of 1. It almost feels like the way that you even define what you mean by volumes in higher dimensions is going to be rested in that fact in some way. So in 2 dimensions, when we say the volume of a unit ball is pi, what we're saying is the area of this circle with radius 1 compared to the area of this square that kind of sits in the upper right quadrant, that's going to be pi. Or up in 3 dimensions, when we say that volume of a unit ball is 4/3 pi, we're comparing the volume of this big cube to the one in the corner. So that's one way you could do. At least for me, I know that doesn't really give me all that much. But there is one way of thinking about the meaning of this volume of a unit ball that is related to the other example that we saw earlier on, where let's think about that counterintuitive setup that I gave you, where you've got a cube that's 2 by 2 by 2, and we're putting unit balls on all of the corners. A question you could ask is, hey, what's the ratio of the volumes here? If I take all the volumes of all of those unit balls on the corners, and I compare it to the volume of the cube, what does that look like? For example, in 3 dimensions, what you end up getting is going to be, well, we've got 8 of those balls, right? So it's going to be 8 times the volume of a unit ball. But the thing we're dividing by is also 8. That's the volume of the cube on the inside. So if we're trying to make sense out of what does it mean, what does it geometrically mean that up in, say, 100 dimensions, the volume of a unit ball is small, I can say, whatever this diagram should be, that I cannot illustrate accurately at all, right? Whatever it should look like in 100 dimensions, if you were to play this game of adding up all of the balls on the corners, all of their volumes, and you divide by the volume of that big cube. So you're basically saying, in this picture, how much of it is cube, how much of it are those corner spheres? The result is telling you almost none of it is the corner spheres. Those corner spheres are nothing compared to the cube. And this kind of makes sense, actually, in terms of the other loose heuristic picture that I was giving, where you have this box that, OK, I can't draw in 2 dimensions, but it's something where the distance to the edge is much smaller than the distance to the corner, so that inner circle has to look enormous. It's something where you have a whole bunch of corners, 2 to the n corners all around. This fact about unit balls, and specifically that they are, in some sense, much smaller as you get to higher dimensions than down in the familiar ones we have, is telling you that in this diagram, those ones around the boundary, they're almost nothing, right? They're almost nothing, which maybe makes a little bit more intuitive, this idea that that inner sphere that you have can be enormous, that it can even poke outside of the various bounding boxes you might try to give it. So with all of that, I thought I would just leave you on one small thought here, which is how sometimes the most beautiful facts about familiar objects, and whether those familiar objects are balls and spheres, or if it's things like the factorial, they can only really be appreciated if you broaden your view beyond that familiar. In this case, to higher dimensions. In the case of the factorial, what are half factorials? And I should hope that this encourages you, that sometimes if you have a little bit of playful whimsy, even if you're not entirely clear what the application is going to be, taking a moment to step back and say, how does this generalize? Sometimes that will give you a little bit of insight about the things that are most useful and that you are most familiar with. So I'll call it there. Thank you very much, and we'll turn to Q&A. All right, thank you, folks. How much do we have more time? Is there time for Q&A? All right. We've got a couple microphones in the aisles. So there's a microphone here, there's a microphone there. I think the most appropriate way to do this is to line up. And then I will rely on someone else to flag me down for when I should stop. Just give people a little bit of a moment to queue up as they want. And then I will toggle between the left and the right. Oh, how exciting. All right, let's start on the right.
Okay, yeah, I'm glad you talked about the zero-dimensional case. I just wanted to point out also in the probability example, what happens if you choose zero numbers and you want the sum of their squares to be less than or equal to 1? The probability is 1.
Ah, I like that. I like that. So for those who didn't hear from Donald Knuth, the interpretation for zero-dimensional volumes comes from asking the same probability question. You choose zero numbers, what's the probability their sum is less than 1? All right, let's go on the left here.
Hi, I really enjoyed your talk. So I kind of have a question that's like a little bit about math education.
Okay.
So, the first time I was introduced to, I guess, like higher dimensional geometry was when I was in like middle school, and I had a teacher have us see this movie called Flatland. I don't know if you've heard of it, but yeah, it's awesome. And I mean, there's also other examples of like movies that talk about higher dimensional geometry, like Inception, for example.
Mm-hmm.
And of course, like these aren't like rigorous sort of ways of thinking about higher dimensional geometry, right? But they like help you, I guess, like gain intuition for what that is like, right? And I mean, I know you kind of talked about this in your JMM talk in January, but like, how do you kind of, I guess, balance the like pedagogical clarity of explaining something like that versus like the rigor of it?
It's a good question. I feel like a lot of the things describing higher dimensions, sometimes maybe it's trying to speak to an itch that certain nerdy high schoolers have to like really hold it in their head. What does it look like? And the thing that always spoke to me is when it feels like it touches an actual problem. Like whatever results you find, you can use it for something. And so to each their own. I think sometimes there are facts where simply the fact that there are strange monsters in higher dimensions. You ask about all of the polytopes in 4 dimensions. The answers that there are being bespoke to that number of dimensions is in and of itself interesting in the same way that like going to a zoo is interesting. So that definitely speaks to some people. But I know that also for others, just knowing that it connects at least in some way to a problem that you can solve actually sinks it and makes it feel real, because there are, at least I've seen like comments on the internet, talking to various students, sometimes complaints on like, wait, but is this real? And that's a perfectly reasonable question a student could ask if you're trying to pontificate to them about the volume of a 100-dimensional ball. All right, on the left side.
Hi, thank you for the talk. On a kind of related note, how would you kind of argue to a random person on the street that it makes sense for people to learn about and study like high-level math ideas like high-dimensional spheres?
I mean, for the person on the street, you know how this was a choose-your-own-adventure talk. I would have taken the other fork in the road. I think, yeah, I think talking about like the relevance to, I mean, AI provides a really nice example these days just because it's so very mathematical on the one hand and very high dimensional. Like its whole way of operating is centered in high dimensional vectors, and getting it to work benefits from intuition about the geometry of those vectors. So the fact that touches a thing that everyone will have heard of, that everyone uses in some way, for the random person off the street, and evidently not for the voting member of this public, I think that's the way to go. All right, on the right side.
Hey there, Grant. Thank you very much for this beautiful talk, a wonderful introduction of a beautiful result. And while I was listening to it, I realized a kind of surprising conclusion, which is that if you sum all the volumes of the even-dimensional spheres,
Yeah.
you get e to the pi r squared.
Oh, it's so good, isn't it?
Yeah.
Yeah.
Is there an interpretation of this fact? Like maybe
I don't
you can
know,
think of
man.
it as a Gaussian process or something?
So there's one, at the very least, there's a delightful puzzle that uses this fact as an answer. I made a number file video about this one, actually, where you contrive a certain variation of the game darts, and it's contrived in just such a way that you ask a certain probability question, and the way that you need to answer it, even though it's all like 2-dimensional darts, you find yourself asking about summing together volumes of even-dimensional, higher-dimensional balls, and so the answer it has like e to the pi fourths, something like that. So you can turn it into a question if you want. Somebody in the room who's smarter than I am might be able to point to like a way to interpret the fact, like what should it mean to add all of them up. So aside from these sort of probability questions where like expected value questions often involve look like adding up a bunch of probabilities here, I can't think of anyone that's like outside of that little playful puzzle. But I can send you the video if you want and the puzzle, because it's, again, if you're looking for a fun afternoon, just getting that puzzle, it's pretty good.
I'd love to see it.
All right, on the left.
Yes, thank you. Thank you so much for the talk. I think it was amazing. And all of your videos, big fan. I wanted to ask how, if you can maybe tell us a little bit how you like plan these videos and this talk. Like, it's a difficult topic. I've taught maths. How do you decide what to include, how to include it? Maybe, yeah, tell us a little bit about that.
Sure. I mean, you're certainly witness to the fact that I'm easily succumb to nerd sniping, which I don't know. There's certain things that like capture my interest. The nature of because the thing I do is make YouTube videos as opposed to other kinds of output you might have. I think it benefits from me being obsessed because an audience might resonate with that. So I could be using that as rationalization. But the idea of like, am I genuinely interested in it? That's a good indicator. But also, if I try to talk to various friends, especially friends who aren't necessarily mathematical, and I try to like pitch it to them, do they seem interested in it? That's usually a good indicator too. But as far as planning the topic out itself, I think there's no one answer here other than you can never you won't find any harm from sample lessons, right? Like if you want to teach something, you want to make some content about something, sit down with an actual person and actually teach it to them, like talk out loud, like draw the pictures you plan on drawing, and pay close attention to how they respond to it. That then informs whether you're writing up an article, making a video, doing a lecture, whatever it is you're doing, having at least one time that you do that, preferably more, with an actual person, it just makes a world of difference, because where they're confused is going to be different from what you expect. Where they're interested is going to be different from what you expect. So it's well worth the prep time in terms of the number of hours that it takes, which is not that much, to the impact that it has for you. All right.
Hi, thank you for the talk again. And I was just wondering, one thing that I really love about your videos is how you incorporate music as a part of the video, besides the math. So could you maybe talk about how you, because I know you compose some of your music, and also how you decide which soundtrack to incorporate?
Yeah, music is a tricky one, because optimally, people shouldn't even think about it being there. Like, if someone's paying attention to it, it's already too distracting. And there's comments to this effect, definitely, like, why are you distracting a lesson with some kind of music? So I try to keep it subtle. For me, I try to use it to establish, like, an emotional undercurrent. So if there's a bit of a tone shift, like maybe there's one part of a video that's just set up, right? Here's just things you're going to need to know, but it's not the exciting part yet. And then the next part, in this case, like the knight's move. Okay, like, how are we going to make sense? You both want to recenter someone to saying, okay, like shake yourself out of whatever state you were in, and also communicate, like, I promise you, this is where it's going to get good. There's certain soundtracks that I think maybe do that a little bit better than others. And so I try to use like the shift from one tone to another to try to communicate without having to do it in words. But I don't know, people are mixed. Some people hate the music, so it's a little bit divided.
I use your music as study music.
Oh, okay, very good. All right, this side.
Hi, thank you so much for presenting for us today. I'm interested in communicating kind of technical or complex ideas to public audiences, so this was like a really cool talk to watch. And I was just curious if you could share some of your maybe like biggest lessons you've had as an educator trying to especially take something as for the layperson, like math is very intimidating, advanced math is very intimidating. I was just wondering if you could share some of your biggest lessons throughout your journey as a math communicator.
Sure. It's a big question. I would say the more specifically you can know the audience member, the better, right? Like the best form of teaching is one-on-one, and then you can respond to what is that actual student interested in. And that, I think there's never going to be any substitute for that. And so if you're thinking about something that's meant to be broader, it actually suffers from a desire to reach a more general public. Like actually a talk like this is quite hard in some sense, because the brief for it is it's public lecture, kind of math department reaching out to the broader public and bringing them into the field. On the other hand, you kind of realistically know a certain prototypical person type that might be coming to attend. And so you know you want to keep the floor low, right? Unequivocally, have to keep the floor low. I don't think I do the greatest job with that always, but I do try. But then, you know, there are certain circumstances where maybe you want to make sure there's something interesting in there, even for someone in the know. And that, you know, I think it can be just a game of like trying through many different ideas and seeing which one of them fits. And then for the floor being low side, just playing the game of every time you, let's say you're writing something, for every noun in your article, just make sure that the reader has reason to understand what that noun means, right? And if they don't, either don't use it, right? Or just make sure it was defined earlier. And you can play this, it's almost like a game of compiling your article or something. Where you go through like, okay, here's a noun. If it's a bit of jargon, like, does it deserve to be there? Maybe yes, because part of the thing you're teaching is the terminology of the subject. But just really make sure that they have every reason to know what it means. And so sometimes just defining it isn't enough, because if you just quickly like blast through the definition, if it's the first time someone heard it, it might not stick. So like really thinking about when would this have sunk into someone's head? Like that little exercise can go a long way. I mean, yeah, it's a huge question, but I'll throw that out as one principle.
Thank you.
Over here.
Hi, thank you, Grant, for this absolutely wonderful talk. I was curious, which topic took you the longest to figure out how to make it into your usual digestible style for the public audience? And is there a topic that you want to teach or make a video about that you still haven't figured out how to make it into a digestible style? I can't imagine you having an answer to that question, but I was curious.
It's a good question. I don't know if this is the answer, but I mean, the most recent videos that I've been making have been about the Laplace transform. But it's been a request for a really long time. So if you look at the gap between like when were people requesting it and when did I actually make it, like empirically that would suggest maybe that one took. Now it's not like I was spending that whole time like, gosh, how do I explain the Laplace transform? But the hard part about that one I do think is that it's again like the target audience thing. The way you might explain it to someone interested in the math theory of it is a little bit different than the way that you would imagine an electrical engineering student would want to understand it. And so I think maybe the unlock there was to just cast aside a desire to like speak to both and just more unequivocally being like, you know what, this one I'm making it with an engineering student in mind. I'll have like a separate video that's kind of what I would tell to the math student, but not trying to like play both sides at once was an unlock. As far as topics that, okay, another one that's actually been on the list forever. I made a video about the Riemann zeta function way back when, but really only talking about just how is it defined and using it as an excuse to talk about this thing called analytic continuation. But the whole reason people care is because of its relationship to prime numbers. And I've always wanted to do just a really good description, making it as accessible as I know how, like how it's connected to primes. And the hard part with that is that I think to actually do it requires at least a little bit of complex analysis, which is fine. It's very beautiful. But it's something where, like, it's not going to be for the lay public per se. But I do want to make it as understandable as I can and not say, like, all right, you need this semesters of background before we can understand the premises. And I think it's doable, but it's just a matter of, like, sitting down and figuring out the way to do it. I don't know. I have a whole long list of topics, so you can find me after. I can pull up the list or something. But there's many, many on there for sure.
Well, yeah, thank you. I just want to say, as an engineer, your videos have been very helpful, and I also want to thank you for inspiring a whole generation of teachers and future educators.
You're so sweet.
I'm getting into it.
Nice. Okay. I believe, do we have 10 minutes worth of? Yeah. Okay. I'm happy to keep answering questions if people are game. But let's go with this side.
Yeah, I also wanted to like extend that like gratefulness of inspiration and all. You visited my high school like 3 years ago.
Oh, fun.
And gave a talk there. It was really inspiring. And I actually got a photo with you. It's been my screensaver for 3 years. And then like my actual question was, I love this talk, and I also want to hear what the other one was. Will that ever be publicly accessible?
Is that your question?
Yeah.
No, we won't. I can give you a high-level description. So, okay, at the very high level, there's a couple facts about not just what's the volume of a sphere, but where is that volume. So, for example, almost all the volume of a ball in higher dimensions is right next to the surface. So almost all of it's right next to the surface. Or on the surface of it, almost all of that volume is just right on the equator. This is a little counterintuitive, especially when you make it quantitative and you ask, how much of it is like within 1% of the height of the sphere from the equator line. And that fact actually ends up being relevant if you want to think about when large language models store words or process words. They turn each one into a big old vector. And it would be very helpful if you could somehow encode different concepts as perpendicular directions in the space that it embeds them into. Like maybe there's one space that corresponds to masculinity of a noun, or one space that corresponds to the word being in French. But as you start to think in those terms and try to read if there's interpretability that makes sense in those terms, while these models put words into a very high number of dimensions, like 10 or hundreds of thousands of dimensions, it starts to feel very small because you would want one concept for each dimension available. But if you ask the question, okay, how many vectors could you cram into a space where they're not all perpendicular to each other, but they're just nearly perpendicular to each other, that turns out to have exponentially more available to it. And this, a way to understand that fact can come from understanding that most of the volume of a sphere is near the equator. So that was, I'll probably make a video on this at some point, but that was going to be the vibe of the path not taken. Yeah. All right, over here.
Thank you for this absolutely amazing talk, Grant. I'm a material scientist, and well, too big. I study material science, and the most I deal with is like two-dimensional, three-dimensional things, and it's so amazing to hear about the world in higher dimensions when it's talked about in math. And the question I have is, so I don't study math, and this might be a really stupid question, but when we were talking about the volume of the unit ball, it was discrete at first, but somehow when you connect the lines, it can be continuous.
Yeah,
so
yeah.
does 2.1 dimension make sense, 2.2 dimensions? So do they make sense?
That's a good question. I mean, so the function being graphed here is the one drawn, but where we're using the generalization of the factorial function that is, however many slides back, where I, this probably, yeah. So this makes sense for any real number. So this you can say, if this is what we want the factorial to mean for any real number, then the formula that we have, it could make sense. So I was just graphing it to have a nice loop there. I do not know off the top of my head if there is like a sensible, what does it mean to talk about a 2.5 dimensional ball? Again, someone smarter in the room might have an answer. Because usually when people talk about fractional dimensions, it's in the context of something called fractal dimension. But that, I don't know, I'll have to ponder if there's any sensibility to. So I mean, these kinds of terms, as one of the people asking pointed out, you see them in the expansion of e to the x. And the maximum of it, you can kind of think like, at what point does the denominator start to beat the numerator, right? And I also don't have like a crystal clear interpretation for how you think about that 5, but in some loose sense, you're playing this game where each time that you step up, you're adding 2 pi to the numerator, but then you're dividing out by n because you're doing the Knight's move and then you're integrating. And so that integrating, it's a little bit like building a pyramid where like if you build a triangle, you're integrating a bunch of lines and you have this factor of 1/2 that comes up. If you're building a pyramid, you're integrating a bunch of 2-dimensional things and you get this factor of 1/3 that comes up. If you do the same in 4 dimensions, you get this factor of 1/4. And that comes from like integration. And so you've got these competing factors where on the one hand, as you go up in your dimensions, you're kind of integrating these boundaries. And so that's giving you this thing on the denominator. But with each step, you're picking up this circumference of a circle. And at one point around dimension 6, that integration factor on the bottom just starts beating the pi on the top. As far as if there's like how to interpret the fact that the 5-dimensional ball is the biggest, I don't have like a clear answer there. But loosely, that's how you might hold it in your head for like, you've got these 2 competing factors. One of them starts to win, and it starts to win by a lot. Was your question also completely answered?
I think so.
Good. Okay.
Thank you.
On this side?
Hi, thank you so much. The question I had is kind of the way you broke it down is like the Knight's move, right? You take 2 dimensions and you hold them separately, and then you treat the rest of them and you show the area, like the boundaries the same. Why specifically 2? Is it possible to do a Knight's move with like a sphere taken out, or?
Well, because I mean, what's going on here is we're using that Archimedean trick, right? And so the Archimedean trick was taking the sphere and then along a bunch of 2-dimensional slices, you're stretching it out. And so why 2 in this case? So if you've got these circles, you've got one dimension where the stretching can happen, but then along this perpendicular direction, that's where you're kind of casting a shadow. And so you've got these two factors that cancel out. If you tried to do that differently, right, where it wasn't circles, then you wouldn't have the same amount of stretching. Like, let's say you were taking something where instead of circular slices along like 2-dimensional planes, you're up on like 10 dimensions and you're taking like 3-dimensional cross sections, and you try something analogous to this. What would happen is that you would have more total stretching that happens because you'd be stretching in 2 dimensions, but that wouldn't be accounted for by that direction where the shadow is being taken, if that makes any sense. And so you specifically want to so that you get exactly that cancellation. If you didn't, you wouldn't have the volume preserving nature of this map from the boundary up to the cylinder, or the generalization of a cylinder surrounding it. Does that make sense?
Yeah. Thank you so much.
Okay, great. Over here.
Hi, thanks for the great talk. So going back to your definition of the factorial, I noticed it looks very familiar to a Laplace transforms definition, which is what you talked about in a recent video. I was wondering if you had any intuition on why they're so familiar?
That's a good question. I don't, in terms of like, so I mean.
We can't see your screen, by the way.
Oh, I see. Wow. Wait, was I just gesturing at the, man, I had the perfect visual for the last question I was answering. Oh, well. Yeah, you're totally right, there is a connection. Okay, this isn't going to be a great end. Let's talk a little bit after, but the way that you can prove why this is true, it just looks like integrating by parts in a certain sense. And then that same integration by parts trick, with a Laplace transform, one of the main reasons it's used in studying differential equations is that when you take a derivative of a function in the t domain, it looks just like multiplication by s in your transformed version. And that fact comes from basically the same thing that's going on here. And so in some ways that, like, you know, integration by parts trick, picking you up all of the factors that you need for the n factorial, it's in the same way that, like, that factorial is going to show up with the power rule applied multiple different times, you know, if you take the nth derivative of a t to the n term, right? So they are kind of the same thing in this context. But if there's like a deeper connection than that, I don't have like the crystal clean answer. I'm like, but of course you should expect factorials. I mean, at least in my mind, the factorial is there for the same reason that, like, if you just keep differentiating something, like, you know, you'd want the factorial to get there, if that makes any sense. This side?
Hi, thanks for the great talk. So when forming this video, or not video, when forming this talk, did you start at the proof for the volume of the sphere? Because I see like remnants of a proof here. And then if you did start there, when did you decide to sort of deviate, go visual? Like, how did you go from proof to this?
Well, like I said, I was just nerd sniped by Ravi. But because I mean, it's one of my favorite proofs, that whole Archimedean argument. Well, I won't show it, but yeah, that whole Archimedean argument for the surface area of a sphere. Because it actually comes up in a couple different contexts where, I'll give you a fun one, a different place where that same like fact is kind of useful. I know. I'm preparing the right slide for you. Okay. So here's a fact where it comes up that we wouldn't think it does. Let's say you've got, you're going to choose 2 random points on a sphere, 2 random vectors on a sphere, and you're going to take their dot product. So kind of you project one onto the other. What's the length of that shadow in a signed way? A natural question you might ask is like, what's the distribution? Sometimes it's positive, sometimes it's negative. You know, does it tend to be closer to 0? Does it tend to be farther away from 0? And it turns out, through many slides that I won't talk through necessarily, but basically using the same like area preserving nature of that projection, like a way you could interpret this is to say if you choose a random point on a sphere, the z coordinate is basically uniform because the probability of falling between 2 given values of z is the area on that part of the sphere. But that's the same as the area on that corresponding part of the cylinder. But that area on that part of the cylinder is just independent of where you were. So kind of surprisingly, you end up with a uniform distribution for this random dot product question. And it uses that same fact. And so this, I don't know, this little like area preserving map, it's one of my favorite facts, and it comes up in a couple unexpected circumstances. So that's just was like on my mind. And then, I don't know, you have this pretty clear connection to then using it towards giving what's nice about that is it doesn't use calculus, right? Like Archimedes did this. He didn't have calculus, but he could find the surface area of a sphere. So you can still use that to talk about this very interesting and non-trivial fact, just with a little sprinkling of calculus with your integration. And so it was a thing that was on my mind and that I had visuals for anyway. And so it was natural to kind of step it up. Yeah. All right.
Thank you again for the awesome talk. I'm actually a high schooler, and I've really been inspired by your videos, and I'd love to pursue math or any adjacent subjects in the future. And I was wondering, what words of wisdom do you have for someone like me?
Maybe embrace that math is a very social endeavor, right? It's often, you have this conception of like person just sitting over their own notebook or poring over textbook, but like you're in high school now, engage with your teachers as much as you can. When you're in college, engage with the faculty. I was a bad undergrad, I didn't do that as much, but looking back, I'm like, oh, wow, I would have gotten a lot more out of my time here if I was like spending much more time with the faculty of my department. And so just really like self-identifying not just as a math person, but as a social math person, I think it can be a pretty big unlock.
Thank you.
Hi, thank you for the talk today. Really big fan of yours. And I wanted to ask, how much time do you devote thinking about mathematics and like making these videos? And
all of it.
How has that changed in the last few years for you?
I mean, the honest answer is probably since the time when I was an undergrad here and now, I probably just care a lot more about the adjacent applied fields. I was just very into pure math for pure math's sake, which is lovely, of course. But I think it's been 10 years since then. Like one of the biggest ways my academic mind has changed is just really enjoying the places where you can see something applied, understanding how to construct something, understanding the motivation for certain problems, connections between different fields. Whereas my younger self was maybe a lot more interested in like, as a pure puzzle for pure puzzle's sake, like this is just delightful, right? And there's of course room for that, but it's a shift.
So this is just a very silly question, but have you practiced pool since playing with Matt Parker? And are you still projecting the ball into the imaginary pool tables off to the side?
No, I haven't had much occasion for pool. Yeah. All right, I think we have time. Let's do 2 more questions, and then we'll call it. And I'll stick around to say hello to folks. Who's on this side?
Hi, I'm a really big fan of your videos. Thank you so much for talking to us. I was wondering if you could apply the same principle that Archimedes did with different shapes, like cones or cubes, etc.
I can't see off the top of my head. I mean, the reason it feels so quintessentially relevant to the sphere, so one of the parts of the argument, when I referenced you do some angle chasing to find that two certain triangles are similar. So that really relies on the fact that the tangent direction is perpendicular to this radial direction. And that's just so quintessentially, like, you're talking about a circle when you're doing that. That's not to say that you couldn't, but just off the top of my head, it feels like the nature of that argument might like lock you into a sphere in particular. But I don't know. You think about it. Like, tell me if you find a way to generalize that in some fun way. On this side?
Wait, first a little comment on the previous question. I forgot if this was in one of your videos or in some math video I've seen, but if you take a sphere, the height is 2r and the radius is r. If you take an upright cone and a downwards cone, then the combined lateral surface area over any interval is actually the same as the right cylinder or the same sphere.
Yeah, that's another really beautiful way to see the 4/3 pi r cubed fact. Yeah. Which is possibly related, but that's another completely beautiful way.
Yeah, but I want to say thank you so much for the talk. I've been watching your videos since like middle school, and I don't know if you remember giving a talk at BMMT 2019, but that was the first time I saw you in person, and it was really cool. So yeah, thank you so much. I was wondering what advice would you have for us to contribute to the greater math community, in particular, just like spread this idea of math being cool and interesting to more people. I know I've talked to Potion Low about this. He's done a lot in this area, and I know there are a bunch of math organizations, a few that I'm part of, that do this. But I was wondering what your thoughts were.
I would encourage anybody who's into math to have some part of their life be a little bit of teaching, especially like one-on-one tutoring. Like, These days, one of the things I do with my life, I tutor my 6 and 8-year-old niece and their friends. And it's very different from the kind of things that I'm talking about here. I love it. It is so great. And it also feels pretty high impact, where the role that you have in like a one-on-one context is just so different from like content creation. And everyone in this room is probably just way more savvy with math than the average bear out there. And it feels almost like a waste not to use that just a little bit, given that it's going to bring you delight to like find a young person in your life and then just say, hey, let's have math lessons once a week, right? Like that's such a great exchange of knowledge, and then most of us just don't do it. And it's probably pretty high impact too. So I think like trying to focus on the things that are not, okay, how do I reach the most people, but saying, how do I reach a given person, but really deeply. Because if you ask someone why they like math, if they do, you ask a mathematician what got them into math, so often the answer starts with like, oh, well, there was this one teacher, right? And then they tell some story. And that tells you everything you need to know about where the influence actually happens. So if you don't, teach. Find someone to teach.
Thank you.
Let's actually, because you're all standing there and you've waited so long, let's do a real rapid fire. So if you could like just state the sentence and then in one sentence question, and then I'll give a one sentence answer for the remaining ones.
What's the application of this to the complex numbers?
I said that, and I'm going to ask you. Could you say that again?
What's the application of like thinking about the volumes of a like multi-dimensional sphere to like complex numbers?
So okay, the question is application of volumes of spheres to complex numbers. I know there's a good answer there. I'm going to say I don't know off the top of my head, but let me think for just, because there's definitely relations there. I don't know. I'm sorry.
You might not be able to answer this in like one sentence, but how do you foresee LLMs like helping math research / math education?
Well, you should reach out to the researchers here and ask them how they're using it. Education conditioned on motivation seems amazing, right? But most education tools, like explanation is different from motivation. And it's not clear to me how it's as helpful for an unmotivated student. So if you want to think of like using it to revolutionize education, you have to think about motivation. But conditioned on a student being motivated, it's a huge unlock, and it's great. Over here.
Have you ever attempted to or thought about creating like higher dimensional models of like abstract forms or non-geometric forms, like the way you go from cube to hypercube to two-dimensional representation of hypercube on a screen, doing that with like three-dimensional form of a human to like a fourth-dimensional human model to a projection of that on a screen, and just thinking about like, I think that's interesting to imagine what it looked like and like what the implications would be.
Your question started with the words, have you thought about? The answer is no. All right. That's all I have. I'm sorry. Thank you, everyone, for coming. This was great. All right. I'll stick around to say hello, but have a good night.